All right, so we're going to look at example 1. What is the sequence of the first differences for the linear polynomial given by ax plus b, where a and b are constant coefficients? So first off, we need to understand what's being asked here. It asks us for the sequence of first differences. So if we're looking for first difference, we can look back at our graphic and we notice that the first difference is the third column. So if we're building a table, much like the one above, we're going to need 3 columns in order to get our first difference. So before we do anything, we can quickly build a table. With 3 columns. Then let's look at the rest of this. It says, what is the sequence of first differences for the linear polynomial given by ax plus b? So let's look at that piece right there. Linear polynomial given by ax plus b. The reason why we're going to be using ax plus b here is because we want a generic polynomial. We don't want to have any numbers in there whatsoever, because if we add any numbers into our expression, then we're only learning things about that particular expression. We want to know about all linear polynomials. So anything in this table is going to tell us anything we need to know about linear polynomials, because we're only using ax plus b. The last piece, where it says where a and b are constant coefficients, all that's saying is that a and b should be numbers. If it was an actual linear polynomial, you would see numbers there. X is different. It's our variable. So we want to differentiate between the two. So x being a variable and a and b are going to be considered constant coefficients because there should be numbers there. All right, so let's look at our table. Just like the table before, we're going to have a number. We're going to have the output, what we're doing to that number, and then we're going to have our first difference as our column headings. So we've got our input number. Let's call that x. We've got our output, which we're going to say is ax plus b, and we've got our first difference. We need x values, so I usually like to start with 0 and count forward. We want these, for this particular idea, we want our numbers to be sequential and only 1 digit apart. So I'm going to start with 0. I'm going to go to 5. All right. What we're doing here is we are plugging in values of x into our expression. So we have ax plus b. If we were to plug in 0 into that, we would have a times 0 plus b. Notice that a times 0 is 0, and then whenever you add b to it, you just have b. So we can put a b there. If I were to change that 0 for a 1, I'd have 1 times a, which is a, plus b. So we have a plus b here. Continuing, I can put a 2 in for that x, and we have a times 2, which is 2a, plus b. And we can follow that pattern down, because you notice it's going to just go a, 2a, 3a, 4a, 5a. All of them are added to b. All right. Next, we've got to figure out our first difference. And there's 2 ways you can go about getting this first difference. They're both subtraction. I'm going to first show you the kind of longer approach here. We could write this out and we could say a plus b minus, and I'm going to always put that second thing in parentheses because we're subtracting the whole thing, b. This one's relatively simple because a plus b minus b is very easily seen as a. And I'm actually going to change my color here for the first difference. So we're going to have a there because the b minus b goes away. If we want to do the next one, it gets a little bit more complicated here, and we have to be a little bit more careful. A plus b, 2a plus b minus a plus b. We need to actually distribute that negative through to give us 2a plus b minus a minus b. And now we can subtract. The b's again go away, and 2a minus a gives us a. I don't like doing it this way because it's, first off, a little bit more writing in order to not make mistakes. And secondly, there's an easier, quicker way, and I'm going to show you that real quick. So if I wanted to do my next step, let's say 3a plus b minus 2a plus b, I can subtract straight up. So if I start with 3a and I subtract 2a, 3a minus 2a is a. And then we notice here b minus b would go away, so we would just be left with a again. That's the easier way to do this kind of math. Same idea, 4a minus 3a is a, b minus b goes away, and then for the last one, 5a minus 4a is a, and then b minus b goes away. So again, we're left with a. So here, we notice our first difference is constant. I'm going to take us back to the beginning of our discussion whenever I talked about the ax plus b. Why were we using the ax plus b instead of something like 2x plus 4? We're using the ax plus b to describe all linear functions. If I was to use something like 2x plus 4, I would only be describing 2x plus 4 because the numbers constrain us. Here, anything that's in this table is true for all polynomials. All linear polynomials, I should say. So for instance, if I did want to use 2x plus 4, I know that my first difference in 2x plus 4 is 2 because a is equal to 2. First difference in the table is a. Doesn't matter which step you have, it's all a. So therefore, I can say that 2 is my a value, 2 is my first difference. This is how this works. No matter what linear polynomial I use, it will be absolutely correct in the table that we just created. So we can say if the first difference is constant, then the function is linear. But what about the second differences of ax plus b? Well, we notice that the first differences are all a. So if I was to find the second difference for a linear polynomial, then what we would have is a minus a, and that would be 0. So anytime you go past that constant difference, everything after that will be 0. All right.